everyone, myself Dr. M. Lakshmi Prasad, working as a professor in CSC in Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about the graph traversals and algorithms, a question bank on that. So the very first thing is that discuss about breadth first search graph traversal. So discuss about breadth first search graph traversal, otherwise what we call it as a BFS traversal. So BFS is meant for breadth first search graph traversal. So normally a graph is going to have different types of traversals. So graph is nothing but a collection of vertices and edges, and the graph traversal will be of two types. So DFS and BFS. So BFS is that breadth first search, and DFS is for depth first search. And normally these graphs are going to be represented in two ways. So first one is that adjacency matrix representation and adjacency list representation. And another thing, one more thing is that incidence matrix representation. Okay, so the graph is nothing but a collection of vertices and nodes, and the graphs are going to be represented in three ways. So first one is that adjacency matrix, adjacency list, and incident matrix. And so the graph traversals will be of two types. So first one is that depth first search and the breadth first search. So normally if I'm going to have a graph, so this should be a representation of the graph. So what we called as vertex V1, V2, V3 and V4, and these are all what we called as edges E1, E2, E3, E4 and E5. And the graph is going to be presented as set V, E. So where V should be V1, V2, V3 and V4, whereas the edge should be E1, E2, E3, E4 and E5. So what is this? First one is that breadth first search traversal. So the breadth first search traversal of the graph is going to produce a spanning tree as a final result. So spanning tree is a graph, so without having any loops in that one. So normally for implementing this breadth first search, we are going to be use Q data structure. So with maximum size of total number of vertices in the graph to implement this. And in order to represent a queue here, so queue is nothing but a data structure which is going to be hold the values, so which is going to be followed first in first out principle. And here what kind of operation is going to be performed here is that NQ operation, and so here it should be NQ and then DQ operations is going to perform. Okay, and here the NQ is going to perform at rear end, whereas the deletion operation is going to perform at front end. So this is the Q data structure. So by making use of this Q data structure, I'm going to be operate this BFS traversal of the graph. So in order to find the spanning tree. So spanning tree is nothing but a graph which is going to have any kind of the loops here. So what should be the algorithm for this? So algorithm is that, so first we have to be define a Q size for total number of vertices in the graph. Suppose I'm going to have a graph, so first we have to define the Q size, how many number of vertices are there in the graph, and then we select any vertex as the starting point of the traversals. So among this graph, I'm going to choose any one starting point. So this one I'm going to consider as a starting point of the vertex, and we have to visit the vertex, okay, and insert it into the queue. So we have to visit one vertex, and whenever I have found a new vertex, that one is going to be insert in queue here. So let it be V1, V2, V3 and V4. So V2 is going to be inserted into the queue. Okay, and so visit all the non-visited adjacent vertices of the vertex which is at the front of the queue and insert them into the queue. So what are the vertices that are adjacent to that vertex V1? So those are all going to be inserted into the queue. Okay. So whenever there is no new vertex is going to be visited from the vertex, so which is at the front of the queue, we have to be deleted the vertex. So whenever that means that so initial vertex what I'm going to say V1 and adjacent vertices should be V2 and V4. So whenever this vertex, no adjacent vertices are going to have a V1, so we have to be delete that queue first. Okay, so that is the step 4. So whenever there is a new vertex to be visited from the vertex which is at the front of the queue, so we have to delete that vertex. And next one, you have to repeat the steps until the queue becomes empty. So these two steps should be common and we have to repeat this entire 2 steps. So until the queue becomes empty. So whenever the queue becomes empty, then produce the final spanning tree by removing unused edges from the graph. Okay. So this should be the algorithm for the search of the graph. Okay. So we have to be considered and we have to be define a queue. Okay. And we have to be choose any one non starting vertex. So we have to be find what are the adjacent non-visited adjacent vertices. So that one is going to be inserted into the queue. Whenever there is no new vertex to be visited from the vertex, then we have to be delete the queue, delete the vertex which should be at the front of the queue. And we have to repeat the steps 3 and 4 until the queue becomes empty. We have to be repeat okay, then whenever the queue becomes empty, then we have to produce the final spanning tree. So consider a graph with the following example. So consider the following graph to perform the BFS traversal here. So from this we have to be select a vertex A as the starting point and visit A and insert A into the queue. So among this graph, so this is the graph that I'm going to be consider. So in this one I'm going to consider A as the starting vertex. So in this starting vertex, so that one is going to be inserted into the queue. So select a vertex A as the starting point, visit A and insert into the queue. Then in second step, so we have to visit all the adjacent vertices of A, which is not visited. So what are adjacent vertices of A? That should be D, E and then B. Okay. So what are adjacent vertices? That should be D, B, E. So that one is going to be pushed onto the queue. And we have to be delete the vertex from the front of the queue. Okay. So again in step 3, what we have to do? We have to consider D here. From D, what are the adjacent vertices? We have to be find out non-visited vertices. So from here, what are the non-visited vertices? A is already visited, E already visited. So there is no non-visited vertices are present from D. So that's why I'm going to delete D also here. Right. So the D also going to be deleted. And so next one is E. So from E we have to be identify what are the non-visited vertices here. So from E, so the non-visited vertices from E is that. So B already is there, and C you have to be that should be non-visited vertex, and F is under non-visited vertex. So those two things is going to be pushed onto the queue here. Okay. So then what I'm going to say next we have to be insert have to consider B here. So from B we have to be identify what are the non-visited vertices from B. So that is C and E already visited, C already visited, so nothing is going to be there. So we have to be delete B also. Okay. So next one, so C, I'm going to check it out. So for C, what are there any non-visited vertices are there from C? So from C, I have already C, F is visited and G is not visited. So I have to be insert G into the Q, right? So visit all the adjacent vertices of C, which is not visited, and insert newly visited vertex into the Q and delete C from the Q. Okay. So if the C is there, so that one is going to be deleted. And so visit all the vertices of F. So in Q, next one is F. So from F, any non-visited vertices are there? No, all the vertices are visited. So we have to delete F also here. So from here, I'm going to delete F also. And next step, so G is there finally. So for G, all the vertices are visited. So uh, so the G also going to be deleted. So after passing one by one, so what are the vertices that are visited here? First, I'm going to delete A. A is the thing. And next, I deleted D. And here B. And here C, F, and G. So those are the vertices that I'm going to delete it, right? So that means A to B is the thing, A to D, and E, E to C, E to G, F, and G. And this should be the resultant spanning tree as well of the BFS. Okay. So once the queue become empty, the BFS process terminated. That should be going to start this process. And finally, what I'm going to get it here, that should be the spanning tree. And next question is that, so what should be DFS graph traversal? So discuss about DFS. So DFS is meant for depth first search traversal. Depth first search traversal. So what is the depth first search? So the depth first search traversal of the graph is going to produce the spanning tree as well. And here the spanning tree is the graph that is going to have any loops. And in this case, we are going to be use this Q data structure. The Q data structure is going to build with maximum size of 12 total number of vertices in the graph to implement this. So what should be the stack data structure? So stack is a data structure in which one end should be opened and the end should be closed. So this should be the open end and this should be the closed end. And the stack is going to be follow last in first out principle. And whenever we are going to insert that one, what we call dash push, and I'm going to delete the element that we call dash pop. So 10, 20, 30, and then 40. So I'm going to use the top pointer. So initially the top pointer should be -1. So when I'm going to insert, that should be 0, 1, 2, and then 3. So by making use of this data structure, I'm going to implement the depth first search, which is going to be results spanning tree. Not that should be the spanning tree should be as the output. Okay. So but for breadth first search, I'm going to use Q data structure. So for depth first search, I'm going to use stack data structure. Okay. So here also the output should be spanning tree without any loops. And what should be the size of this stack means that should be the number of vertices in the graph. So if I'm going to have the vertex like this, so V1, V2, V3, and V4. So if I'm going to have the vertices, so the total number of vertices, that should be the stack size should also be 4 here. So let us consider an example. So what is the algorithm? First we are going to see now. So here the first we have to be define a stack of size the total number of vertices in the graph. Okay, and then have to be selected vertex of the starting point from the traversal. So how we're going to be implemented in BFS in similar fashion, also we're going to do any have to be select any starting point of the traversal and visit the vertex and push onto this stack. So whenever I'm going to identify the starting point, that should be push onto the stack. Visit any one of the non-visited adjacent vertices which is at the top of the stack and push out on the queue. So whenever I'm going to insert a element from the stack, so I have to identify only any one. One of the vertex that should be adjacent to A have to be identified. That means the top of the stack, and that one is going to be pushed onto the queue. And we have to repeat the step 3 only here until there is no vertex is going to be visited from the vertex, so which is going to be top of the stack. Okay, so we have to repeat the step 3 until no new vertex is going to be visited, which is at the top of the stack. So whenever there is no new vertex is going to visit, then you have to apply the backtracking and then you have to be top of the stacking. Okay, so whenever the no new vertex is going to be visit, then you have to be use backtracking and pop out the stack. And repeat the steps 3, 4, 5 until the stack becomes empty. So you have to repeat the steps 3, 4, and 5 until the stack becomes empty. When the stack becomes empty, then produce the final spanning tree by removing unused edges from the graph. Okay, so when the stack becomes empty, then produce final spanning tree and by removing unused edges from the graph. So note that, so backtracking is nothing but coming back to the vertex from which we revisited the current vertex. So okay, so if I'm going to have a graph like this, so I'm going to move in this direction. So backtracking means again how to go back to the original starting vertex. That should be backtracking. So backtracking is coming back to the vertex from which we are going to be reaching the current vertex. So this should be algorithm for DFS. So when compared to DFS and BFS, so that should be same. So first we have to identify the stack size, and BFS we have to identify the queue size. So here also I'm going to visit any one starting point for the traversal. That thing is going to be moved on to the stack or the queue. So these two steps should be common. And the third step is that, so in BFS, we have to be identified what are the adjacent vertices that are adjacent to vertex V. But here, how to identify what are the adjacent, one of the non-visited vertices is going to be identified. And we have to repeat the step 3 until no vertex is going to be visited. So whenever there is no new vertex is going to be listed, then we have to be apply backtracking and then have to repeat the steps 3, 4, and 5 until the stack becomes empty. So whenever the stack becomes empty, then have to be get the spanning tree and by removing unused edges from the graph. So let us consider an example here. So here I'm going to have a graph like this. So in this graph, we have to be first identify a starting vertex. So select a vertex A as the starting point and then push A onto the stack. So this is the starting point and that one I'm going to be push onto the stack. Then visit an adjacent vertex of A which is not visited. Then push newly visited vertex B onto the stack. Okay. So visit any non-adjacent vertex of A. Visit any adjacent vertex of A which is not visited. So that should be B. So that one is going to be pushed onto the stack. So this is the inner vertex I'm going to consider. But what are the adjacent vertices I'm going to have? That should be A, D, E. We are considering in BFS. But we are going to consider only one. That one we are going to consider in BFS. So that thing is going to be pushed on this. And again, next thing. So from B, so what are the adjacent vertex that are adjacent to B here is that E and C. So I'm going to consider C here. So that one I'm going to be pushed on this. And next, so visit any vertex that should be adjacent to C. So I'm going to have E, F, and G as well, but I'm going to consider only one vertex that should be E here. And from E, so what are the adjacent vertices that adjacent to E, that should be a D and F. But here I'm going to consider D here. So D is going to be pushed onto this track. And when there is no new vertex is going to be visited from D, so then have to apply the backtracking. So from D, so I'm going to, all the vertices are visited here only. So that's what I'm going to, I'm applying backtracking. So from D to E, I'm going to have, and from E, I'm going to have whether any new vertex is going to be visited F. So F is there, so that's why I'm going to push onto the stack. From F, I'm going to have whether any new vertex is going to be visited. So that should be G is there. So that's why G is going to be pushed onto the stack. And from G, I'm not unable to find any kind of new vertex. So that's why again I have to perform backtracking here. So that's why I come back to F. From F, I'm going to identify from E. From A, I'm going to identify C. From C, I'm going to identify B, and B to A. So once all the vertices are visited and this stack becomes empty, I'm going to I'm pop the contents of the stack. So Z, so backtracking is performed G here. So that's why G is going to be popped out first. And then again applying F. So F is going to be popped out. And G, F, E. From E, I'm going to pass out. And again E to C. And G, F, E, C. B, I'm going to pop out. And G, F, E, C, B, A. So these are the final contents of the stack. And once that popped out, so the planning tree, what I'm going to obtain, that should be the spanning tree. So that should be the depth first search. Okay. So once I'm going to pop the contents of the stack, so the tree what I'm going to obtain after performing the DFS is the spanning tree. Okay. So these are the topics what I'm going to discuss in this video. So breadth first search and depth first search. So in breadth first search, we have to visit all the comparison I'm going to explain. So depth first search and breadth first search. So in depth first search, the first thing is that so we have to be considered all the adjacent vertices, but here only one of the adjacent vertex is going to be considered. And here in BFS I'm going to use two data structure, whereas in BFS I'm going to use stack data structure. And here level by level I'm going to perform, but here one node at each level is going to be considered. Okay. So both of out of this DFS and BFS both are going to be efficient one. So it's going to be performed only the breadth for minimum spanning tree. The output should be same, but the strategy is going to be different. Okay, so that should be about the depth first search. So depth first search. So the regards to algorithm, so the algorithm is also quite easy. And only the difference is that the steps 3, 4, 5 and is going to be changed when compared to BFS and DFS. So in BFS, we have to consider only adjacent vertices, but the only difference is that we have to consider only one of the adjacent vertex. And we have to repeat the step 3 until we're going to remove the top contents of the stack. And whenever there is no new vertex, the next thing is that we have to perform the backtracking. So the backtracking is not going to be done in BFS. So in BFS, backtracking is not going to perform, whereas in DFS, the backtracking is going to be performed. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.